30 something? 37. 27. 27, the limit as x approaches 0. 5x cubed plus 8x squared over 3x to the fourth minus 16x squared. So it says explore graphically but confirm algebraically. I'm just going to jump straight into the algebraically part real quick. And I'm going to factor what I can because clearly I can't plug a 0 in here, right? I'll have 0 over 0, which is no bueno. So I'm taking x squared out of the top, leaves me with 5x plus 8. Taking x squared out of the bottom, which leaves me with 3x squared minus 16. There's my whole, which is at 0. So I got 5x plus 8 over 3x squared minus 16. So now if I do the limit as x goes to 0 here, I can just substitute in. So I get 8 over negative 16, which is negative a half. 28. Oh, I told y'all to start 28. I bet you would have questions. X goes to 0. One year we didn't get to complex fractions in Algebra 2. Was that y'all's year? All right, I'm just going to do some algebraic manipulation here because I'm dividing fractions by something I'm going to multiply by the reciprocal. So I am going to multiply by 1 over x all the way here. Let's see what happens. I don't know if that's going to help or not, but let's see. 1 over 2x plus x squared. Just to get it in one single fraction. Because it was a fraction, yeah. Dividing by something, same thing as multiplying by 1 over that value. So now I think what I'm going to have to do is find a common denominator. Right? Are y'all with me on that? Is that what y'all did? Anybody? You just looked at the graph. What do you mean? Wait, so what did I do? Yeah. Not the one on top. Flip the one on the bottom. Did you? Well, I think I just, sometimes I just like start doing stuff. But you know, it's funny because on FRQs, you get points for the randomest stuff. So if you just start, I always tell everybody, write something. Even if you have no idea what to do, write something. You might get a point. I'm going to find a common denominator. Some of you may have found a common denominator in the very beginning and combine those two fractions and then multiply by 1 over x. I'm going to do it here. So I'm going to give this one a 2x. I'm going to give this one a 2x plus x squared. So I've got 2x times 2x plus x squared as my denominator over 2x minus. Does that make sense? I just gave each one the denominator over here. So my LCD, remember doing LCDs? Y'all are looking like you don't understand what I did. Yeah, well, and since there's ones up top, it makes it a little bit easier. But what I did was I said, okay, if that's the LCD, I give this one 2x top and bottom, multiply. This one, 2x plus x squared, top and bottom. So my common denominator is 2x times 2x plus x squared. Then I combine my numerators over that common denominator. This ends up being x squared over, I'm going to leave this one factored a little bit, but I'm going to pull one more x out. You see why? So I'm going to make this 2x squared times 2 plus x. Now I can remove my discontinuity. Now I can do the limit as x goes to 0. 1 over 2 times 2 plus x. Should be 1/4. Is it not 1/4? Yeah. It's negative. Why is it negative? Yep, you're right. You're right. Sign error. That's right. It's negative. That one was tough, but it was tough. Notice, though, what I keep saying. The algebra was tough in that. The calculus concept was the limit as you go to 0, right? So that's not tough, but that algebra kills you. If you can manipulate algebraically, you may zoom out some, Khalil. Hold on, I can zoom a little bit more. What else? Does that make sense? Did you have to tour somebody else? I'm sorry. We just worked through 28. Yeah. Did you need that one? Okay. 55 or 25? 55? 34. I'm going to do 34 first since we're right here at it, and then I'll do 55. The limit as x approaches 5. Oh, look at this little difference of cubes here. Did y'all catch that? Yeah, you did. If you have forgotten your sum or difference of 2 cubes, remember this is the one if I have a cubed minus b cubed, then I can do little parenthesis, big parenthesis, signs are same change plus. You do a and b, and then you use this to write your second trinomial. You do a squared, you put them together, and then you do b squared. I can do the same if it's addition, because they're cubes. Still same change plus, if you forgot that one. So up top, I can factor this. I'm going to try to plug the hole if I can. X minus 5 times x squared plus 5x plus 25. The hole has been plugged. So now is the limit as I go to 5 of x squared plus 5x plus 25. $25, $25, and $25 is $75. Which you might have had trouble seeing if you were on your calculator. I don't know. Maybe. Have to adjust the window some, I'm sure. These are fun. Don't y'all think these are fun? Yay, they're fun. I don't think so. Henry, which one did you say? 55? Assume that the limit as x approaches 4 of f of x equals 0, and the limit as x approaches 4 of g of x equals 3. So part A said, bless you. What's the limit? This is just using those properties to try to get you familiar with what you can do and what you can't. So, you fix to say something. So the first property, this is addition, and I can split those limits up. So the limit as x goes to 4 of g of x plus the limit as x goes to 4 of 3. Well, what's the limit as x goes to 4 of g of x? That was given to me. That's 3, right? The limit of a constant is the constant. So this equals 6. How about the limit as x approaches 4 of x times f of x? So this is just 4, right? And I can take that constant and put on the outside. You agree with that? That's one of those ones we talked about. So it's really 4 times the limit as x goes to 4 of f of x, which is 0, which is 4 times 0, which is 0. Bless you. How about the limit? You come right here, right? This is part C. The limit as x approaches 4 of g squared of x. What's that property about exponents tell us? Square the whole thing. That's exactly right. So I'll do the limit as x goes to 4 of g of x, and then I'll just square that whole limit. So this would actually be. Then the last one, gonna need some parentheses here for this one. Limit x goes to 4 g of x over f of x minus 1. So I'm going to do this as the limit of g of x over the limit as x approaches 4 of f of x, and from that I'm going to subtract 1 because the limit of the constant is the constant itself, and then I just plug in. So I've got 3 over 0 minus 1, -3. Does that make sense? Make dollars? Y'all got to work with me a little bit. Give me a little something, just a little something. Okay. What else from your homework? Was it? Everybody good? Yeah. $49? Where it says what? My 49 is a graph. Is that y'all's? And it asks for the limit. F of 0. That's my last one. Do you have the right book? $71. No, don't apologize. It's okay. We just adopted new books last year, so it would not surprise me, though, if you'd gotten a different book. You know what I'm saying? All right, anything else? Going once? Twice? Okay, what time's the bell ringing here today? Oh, I was about to say, no way, 9:30, but not, okay, 9:55. What do you think? Yeah. More limits. Really just examples on how we're going to work with limits and trig functions. What in the world? Y'all contain your excitement. Y'all literally, Avery literally looked at the board and like, I roll with it. It's okay, I get it. I really do. What do you think? I don't see any type of algebraic manipulation that I can do with this. I mean, I could graph that maybe. Let's see what happens if I graph it. This is one of those that will pop up. For some reason, this particular limit right here, it pops up all the time. It'll pop up in multiple choice questions. It'll pop up on FRQ sometimes. I don't know, but this particular one pops up a lot. And sometimes, in fact, most of the time, it's on a non-calculator part. So it's one of those ones that you just have to memorize for some reason. But let's look at it. Sine x. Make sure you're in radians. I'm going to zoom trig, zoom 7 on it. Looks pretty self-explanatory. What do you think? What do you think the limit as x approaches 0 is here? 1. Why is it 1? Why can I assume it's 1? Because clearly it's not defined at 1. We know because I'm dividing by 1. It's getting closer to 1 from both sides. Remember that limit has to be the same from both sides. All right. So this equals 1. It equals 1 every time. I know that was a super easy one, but make sure you have that one. I would highlight that one to see because it keeps coming up. So now let's use that and let's see if we can do a little non-calculator algebraic manipulation to find, remembering this, tell me what you think the limit as x approaches 0 of tangent x over x might be without graphing. We'll graph it in a minute and I'll prove it to you. What can I do? Any idea? Yep. Close. Sine over cosine. All right. So I could say, all right, well, this is the same thing as the limit as x goes to 0 of sine x over cosine x all over x. I agree. I think that's a good first step. Multiply by 1 over x. I'm going to get them in just one fraction. I agree. Great. Next step. Sine x over cosine x times 1 over x. Now remember, when I multiply fractions, I'm top times top and bottom times bottom. So really this is just sine x over x times cosine x. What do you notice? Exactly. I know that the limit as x goes to 0 of sine x over x, I know that limit, right? But what would that leave me with? 1 over cosine x. Agree? Disagree? Agree? Disagree? Agree? And the properties of limits say I can split these up, right? So I could say, okay, well, I know this is 1 times, and now I need to know the limit as x approaches 0 of 1 over cosine x. And you might go, well, dear Lord, I just got myself in the same boat that I was in to start with because I don't know. But what's cosine 0? 1. Your first step is always to try substitution if it works. It works here. So 1 times 1 over cosine 0 is 1 over 1. See how we manipulated that some? I know that right now your brain's not going to go to that, but I'm going to try to get your brain trained to go in that direction as we look at these. If you graph it, you will see that it does indeed go to 1. It looks a little something like, it's a funky graph. This one, by the way, tan x over x. it does something like this. So as I go to 0, it does approach 1 from both sides. Are y'all okay? That doesn't stress you out or anything, does it? Let's try one. That's what? Yeah. Yep. Just remembers 1. This is number 30 from your homework. You're going to really have to think about this. You might need, this is a little hint, you might need a special sheet I gave you. Don't remember some of this. But I'm asked to evaluate algebraically. No calculator. I can't plug in because I got a 0 on the bottom. So I have to think about some way to manipulate, some way to write it a different way. Thoughts? Yep, absolutely. That double angle identity. I could rewrite sine of 2x as, again, look, no calculus yet. Say again. That's exactly right. Yeah. Yeah, look at your identity sheet. Look at that double angle identity. Yep. These don't come up a whole lot, but they come up enough that, especially, there's some that come up more. The double angle identity does come up quite a bit. All right, so Abby said, look, I see the sine x over x already, right? I'm going to break that apart because my properties of limits say that I can do that, right? So I'm going to say this is the same thing as the limit as x goes to 0 of sine x over x times, and then I'm going to put what I got left. The limit as x goes to 0 of 2 cosine x. Agree or disagree? Well, what's the first one? If you were adding or subtracting, you'd have to make separate fractions, but because you're multiplying, it only has to go with one thing. Because remember, if I multiplied this back together, it's top times top and bottom times bottom. I know this is 1. How about this one? Substitute, that's right. Cosine of 0 is 1. This 2 can be in front. So multiplying by 2. Does that make sense? Sure. Yay! Let me give you one to try. Yeah, you can do that. I would get, if you're on an FRQ, you want to show every single step. Multiple choice, which this is probably a multiple choice type question. You wouldn't need to. You try this one. See what happens. Evaluate the limit algebraically. This is number 32, by the way. That's exactly right. That's exactly right. Did y'all get it? Tell me what you did. Split it into two. I got x over x. Boy, that looks familiar. Right? So if they cancel, what happens there? Equals 1. What's the limit of a constant? The constant. So it's just going to be 1. Yeah. So what you have to do, because of this plus, you have to break this into two different fractions. Yeah. If I was multiplying, it'd only go with 1. But if I'm adding or subtracting, it needs to go with that. Yeah. Well, you can't replace it with 0, right? Because if you replace it with 0, you're in undefined territory. So what I have to do is I have to simplify. So what I'll do is I'll say anything divided by itself, 1, I kind of plug that hole. So that's a removable discontinuity there. What else? I remember what we did. Which numbers did I give y'all last night? What did y'all go through? Do y'all remember? I don't know if I want to talk about it. Y'all give me just a second. I'm trying to decide if I'm going to show y'all this yet or not. I think I'll show you. I think I can handle it. Your book calls this the Squeeze Theorem. I always called this the Sandwich Theorem. Both of them, either one. I'll put AKA Squeeze Theorem. And then I'll try to shut up and let y'all do your work. So here's what the Sandwich Theorem or the Squeeze Theorem says. Let's say that I asked you to evaluate the limit as x goes to 0 of x squared times the sine of 1 over x. Or I asked you, actually, let's say I asked you to show that that equals 0. So the sine of 1 over x is different than sine x over x, right? Do we see that? Do we understand that? This is taking the sine of 1 over x. So let's think for just a minute. I know that all the values of sine, any sine value for that matter, fall between what? -1 and 1. They're always going to be between -1 and 1, right? Think about that unit circle. You're never going to get a sine value bigger than 1 or less than -1. Do you agree or disagree? Say you. Okay, good. Thank you. I'll say, please say you agree. Disagree. Huh? So here's what the sandwich theorem says. You take what you know, you squeeze it between these two values, right? And then the reason I do this is because x squared is a pretty basic function, right? If I add an x squared here, then I'm going to do it to all sides, okay? So I'm going to come here, multiply by x squared. I'm going to come here, multiply by x squared. So Squeeze theorem says if the range of values for sine of 1 over x is between -1 and 1, then the range of values for x squared sine 1 over x must be between -x squared and x squared, okay? And let me show you what this looks like graphically, because then maybe it'll make a little more sense, and it looks kind of cool. Let's say I graphed all right, what do we have? X squared sine 1 over x. Doesn't look like it's doing too much, does it? Let's zoom in. In fact, let's change this to, I don't even know if this is going to give us enough to start seeing the oscillation. -1 to 1. Oh, I'm starting to see it. I really want to zoom in some more. Remember, because I'm approaching 0, right? I can't quite see what's going on here as I approach 0. So let me change my window. I'm going to change to -0.1, 0.1, 0.1. Starting to see some of the oscillation. Let me get some of the width off, the height off of it. I'm going to change this to -0.01 and 0.01. Now I can see. Look at what that thing's doing. Do you see it? That's crazy, right? But watch what happens when on this. Are you not impressed? If you keep zooming in, it'll keep oscillating as it gets closer and closer to 0. It just keeps doing that. Okay, so if on this same graph, I graph x squared and -x squared, because I just said that that function should fall between these values all the time, right? Watch what happens when you graph it. Isn't that cool? I think it's called sandwiches in between. Are y'all laughing at me because I'm getting excited? Are y'all bigging on me because I'm like geeking out over this? I think it's really cool. So, I mean, it's completely bounded by those two curves. Even if you keep going in, even those oscillations there. Well, that's the sandwich theorem or the squeeze theorem. We squeeze it between two known functions. We start with something we know, and then we can expand that to find something. So how does this help us to actually solve that problem? I just want to show y'all that because I thought it was cool. Thank you. I really appreciate it. Thank you. Y'all don't have to really think so, but that's okay. So now what I can do is remember the whole reason for this was to find the limit as I went to 0, right? So now if I plug 0 in for these x's on the end, Well, if it has to lie between 0, right, then it must be 0. So then the limit as x approaches 0 of x squared sine 1 over x is 0 by the squeeze theorem. Well, if this value is between 0 and 0, is less than or equal to, because it's or equal to, that means the only thing this could be was 0 to make that true. Well, if I do what's in the middle in 0, I get undefined, and I can't do that because I can't do 1 over 0, which is the whole problem the whole time. So I'm trying to think of something else that I could do. Most of the time it will say you'll have this, I think there's one more, I thought I wrote it down with the squeeze theorem in your book. Most of the time, for right now, it'll say, using the squeeze theorem, what do you think this falls between, until you get used to when you can use it. That's why I was hesitant. I don't remember doing sandwich theorem this early last year, but maybe I did. What do y'all think? Well, you can, but it asked me to do the limit as x went to 0. That was the initial problem. So since I couldn't sub in, and there's nothing really to algebraically manipulate, well, then I squeezed it between. I said, well, I know that this part of it always falls between -1 and 1. So if I do that, and then I put the x squared, could I then plug in for my x's here and know that? And if it had been, let's say it was 1, let's say it was as x approaches 1 or something like that, then all I could say is it's between -1 and 1. I couldn't give a specific value. But if you get the same values on both ends and it has to lie between, then it must have the same value also. Right. Right. It gives you a range of values, but most of the time when you do the squeeze theorem, if you're set up to and asked to do sandwich theorem, it's because you're going to get the same value on both sides. Yes or no? Did we talk about piecewise? I feel like we did, but maybe we didn't. We did. Y'all remember how to do piecewise? Okay. All right. Well, I'll stop then. I could go on to some limits with infinity, but we won't. We won't push it. Stop. I'll give you time to do your homework. I'll give you 20 minutes to do your homework. Let's do. We did some of these together. If we did them, skip them. I know we did 30. Do 31 to 34. I think we did 2 of those. 2 more of those. 32. Okay. Those are trig function manipulation. Actually, you already did 34. Then let's do. Let's do 57, 59. I'm gonna get a trig one. 61, and then 65 to 68. Those are sandwich theorems, but they tell you to find the limit graphically and then use the squeeze theorem to confirm your answer. I think that should be good. Did we do 69 and 70? I don't think we did. With A-Rock and I-Rock? Wait, I didn't give y'all those? Are y'all sure? Let's do 73 to 76. Those are quick. Those are quick multiple choice ones. They're just look at it and tell if what the limit is. And we'll stop there.